In this fifth and final video for the SL07, we'll be talking about why we might want to make acetals in the first place. So there's a couple of answers to this kind of a question. One is that nature makes these in a variety of important biological contexts, and so that's actually what SL08 is about, biochemical molecules that contain acetals and hemiacetals as important functional groups. If we're actually thinking about making acetals synthetically, so like in a lab, they tend not to be the compound that we care about so much as a way for us to manipulate reactivity of carbon. And so it's really the properties of an acetal relative to those of a carbonyl that we'll focus on in this video. So to get started, we'll think about making an acetal, again from a relatively simple molecule, so this will be a little bit of a rehash from prior videos. We could start with an aldehyde like this, dissolve it in some alcoholic solvent, in this case we'll use ethanol, and some kind of an acid catalyst to promote the acetal formation. And so we know that what we would find is that the carbonyl would disappear, and in its place we'd have two different ether groups. So we would have, in this case, a diethyl acetal and a product structure that looks like this. So what I want to focus on in this video is what the reactivity of the carbon that was a carbonyl in the starting materials actually is in the final products. And so this is basically like asking what kinds of roles do you expect. So if I look at the starred carbon here, I know that this site's going to be electrophilic. But if I look at the starred carbon in the product in the acetal structure, it's actually not electrophilic anymore. There's a couple of reasons we can expect this. One is that the carbon's sp3 hybridized, which means that if I introduce a nucleophile to the starred carbon, something is going to have to leave. In a carbonyl, I can just break the CO pi bond, but that's not an option on the acetal. So this is not electrophilic. There's no good leaving group. And so you can imagine that even treating a compound that has this kind of a functional group in it, like an acetal, is going to be resistant to most kinds of nucleophiles, right? So that's kind of the crux of what I want to discuss here, is that acetals are inert, meaning they don't react, toward even strong nucleophiles. So that's important. If I want to actually do selective chemistry, maybe I've got a couple of places in a molecule that could be electrophilic and I want to only actually react a nucleophile with one of those places, I could maybe think about taking one of those sites, if it's a carbonyl, like a ketone or an aldehyde, and I could convert it into an acetal. So doing that takes an electrophilic site and it like hides it, or sometimes we say it protects it from the kind of chemistry that we want to do later, like with a nucleophile. But that's actually not that helpful unless I can reveal the original functional group again, right? So it's true that acetals are inert toward even strong nucleophiles, but it's also true that acetal formation is reversible. Both of those things, so this criteria that they're not reactive with nucleophiles and that you can reversibly make them, means that we can treat acetals as what we're going to call protecting groups. And this idea of a protecting group is something that you can install in a molecule to hide reactivity and then remove later to reveal the original functional group. So let's look at an example about how we would use acetals as protecting groups. Okay, so we can look at a couple of examples where we're actually using acetals as protecting groups. And just to remind you, the goal of these kinds of reactions or syntheses, really, so sets of reactions involving protecting groups, is to temporarily hide reactive sites. For acetals, we're temporarily hiding electrophilic carbonyls. So let's say that we wanted to actually convert this compound, which contains two different electrophilic sites, to this product. So we know that the carbonyl carbon here is electrophilic, and we also know that the carbon with a good leaving group now, bromine, is also electrophilic. And I know that I need to make a substitution change at this site, which means that I want to try to remove electrophilicity from the carbonyl temporarily, install the new carbon-nitrogen bond, and then remove whatever I've done to hide or protect the electrophilicity of the carbonyl. So if I actually tried to do this directly by just reacting this compound with an amine, for instance, I would mostly make an imine. that's not exactly the product that I want. So our synthesis would be first to take our starting ketone and convert it into an acetal. You can choose any acetal you want. There's quite a bit of work that's been done about which ones work best, but you don't need to worry about that level of detail. So I'll just choose to make a dimethyl acetal from methanol. And so that will hide the electrophilicity of the carbonyl. So I've gone from an electrophilic site here to a non-electrophilic site in the acetal. Bromine is going to survive unchanged. So then I can do an SN2 reaction where I'm directly displacing the bromine with some kind of an amine nucleophile. So that will be the amine that I need. This is just an SN2. And that will form the new bond. So I'm now using the electrophilic site that I want. And just to remind you, the carbonyl was electrophilic. It no longer is. And that means that our acetal is still in the product here. And I've made my new carbon-nitrogen bond. So the last thing that I need to do then is to actually remove the acetal, because I'm not trying to make a compound with an acetal, I'm trying to make a compound with that ketone. But now I've already done this chemistry. So I no longer need to worry about hiding the electrophilicity, so I can hydrolyze the acetal here. I need some water, and I need an acid catalyst. And that will actually remove the acetal, convert it back into our carbonyl, and give us the product that we want. So you can see that these types of protecting group syntheses usually involve multiple steps. One step where we're actually introducing the protecting group. So we're going to protect our ketone here. We're going to do the chemistry that we actually wanted to do. And then in particular, the reaction we couldn't figure out how to make selective in any other way. And then in this last step, we're going to remove the protecting group. So that's pretty typical for most reactions involving, or syntheses, involving protecting groups, that they follow this pattern of protect, do your chemistry, remove. So in the next section of this video, we'll look at another example. In this final section of our video, we'll look at another example of acetals as protecting groups. So in this synthetic scheme, what we're trying to accomplish is converting this chloroaldehyde into this final product where we've made a longer chain as well as a secondary alcohol. So if I inspect this carefully, I'm going to follow the carbon that has a chlorine on it into the product. So that looks like it's 2 carbons away from the carbonyl, which would be this carbon here. And I notice that that is adjacent to a carbon where I've made a new carbon-carbon bond. So that's one of the things I'm going to have to do. And that new CC bond is essentially connecting into a carbon that has an alcohol. So this new carbon-carbon bond probably came from some kind of a Grignard reaction. And because of where this alcohol is, if I think about the Grignard reaction, it was likely the case that our starred carbon was the nucleophile, and this carbon that has the alcohol was the electrophile, right? That's going to end up, this carbon here that we're labeling as E is going to end up getting reduced in the Grignard reaction, and that's where the alcohol is coming from. So if I want this carbon to be nucleophilic, well, that's good. That basically tells me that I can take this carbon in the starting materials and make it nucleophilic by treating this halogen compound with magnesium. So I can make nucleophilic with magnesium metal. But the issue is that if I actually do that, if I actually make the Grignard reagent from this compound directly, I'll have a nucleophilic carbon bonded to the same molecule as an electrophilic carbon, and this compound will start to react with itself, right? So basically, as soon as the Grignard reaction or reagent forms, it'll start to react with more copies of the compound that has not yet been converted into the Grignard reagent. And that's going to give me a problem. My yield's going to be 0. I'm going to actually make just a side product. So one of the ways I could solve the problem is by hiding the electrophilicity of this carbonyl while I'm making this carbon nucleophilic. So this is a little bit more indirect than the first example we looked at, where you're just trying to hide one electrophilic site to use a nucleophile on a different site. But you can think about these protecting group strategies as ways to control all sorts of different off-target reactivity, so things that we're trying to avoid. So from a perspective where we would actually propose a synthesis, again, the first thing we want to do is hide the reactivity that we don't want. So we're going to make an acetal. I'll choose a different acetal this time. So we'll use ethanol and an acid catalyst. And that's going to give us a diethyl acetal, like so. Now I'm ready to make my gridded reagent, so I'm going to treat this compound with magnesium metal. Okay, and so now at this point I'm going to point out our roles. So our carbon that we wanted to make nucleophilic now is nucleophilic. And the aldehyde, or the acetal, excuse me, carbon is not electrophilic. So I've solved my problem. This reagent can form, no issues at all. And so now all I need to identify is what kind of carbonyl electrophile I can use to add this whole piece of the product. It looks to me like I can use a 1, 2, 3, 4 carbon unit. The alkene is going to still be there. And because I'm making a secondary alcohol in the product, I know that what I need to do is react this compound with an aldehyde. So the specific aldehyde would be that structure. And I know that I'll need a water workup. Okay, so that's going to give us a compound that still has an acetal in it, but also has the new secondary alcohol and the elongated carbon chain. So now that I've done the chemistry that was incompatible with this carbonyl, the last thing I'm going to do is remove the protecting group to reveal the aldehyde in the product that I want to make, which again is a hydrolysis reaction. All right, so if we go through our steps, again we would identify the first step as being a protection of an aldehyde. And this final step will be deprotection of the aldehyde. So we can see that acetals are a useful protecting group for both aldehydes and ketones and in a variety of contexts. So this concludes the video series for SLO7. Good luck with your homework.